right? So what is a projection? Suppose you have a vector like this. Let's say you have v and u, right? So what is a projection? So essentially this point is the inner product. This vector is your projection, right? Do you agree? So how do you find this vector? Of course, if you look at this is alpha times u, right? So I scale alpha, I get this point. I want this alpha u to be orthogonal to this vector, right? So want alpha u to be orthogonal to this vector. What is this vector? V minus alpha u, right? So v minus alpha u. I want this to be 0. That means I can find alpha such that this is satisfied, right? So that will give me the vector. So what is that? It will be alpha times uv. I've used linearity of inner product minus alpha square times u inner product with u equal to 0, right? So this implies the alpha star will be uv divided by uu, right? So this is what we get. So that means the projection of v onto u, right? So for example, if I want to project, let's say v onto u, right? So this is the notation. So what is the vector that I get? It's alpha star u, right? So what is alpha star? uv divided by uu times u. Is that fine? So note that projection of v onto u is denoted by this. So it's uv divided by uu times u is what the projection is, right? So how do you get the orthogonal vector here? So what are the orthogonal vectors? U is an orthogonal vector. So for example, u, if you take as is, what is this thing? This is v minus projection of v onto u, right? So this difference, these two are orthogonal. Do you agree with this? Right? Okay. So let's try to generalize this. Suppose I have 3 vectors. So what should I do? Given, let's say v1, v2, v3. So what is the first step? So I should get the first vector. I'll take v1 tilde as v1 itself. Okay. So what should I do for v2 tilde? Exactly what I did before, right? It's v1. So v1, so essentially I took u and then I took v2 and project onto v1, right? It will be v2 minus project what on what? v2 on v1. Well, I'll just take it as tilde, okay? Because v1 tilde is same as v1. Is that fine? So clearly v1 tilde and v2 tilde are orthogonal. They are not orthonormal, okay? So they are orthogonal. So how do you find v3 tilde? You understood the procedure, right? So for example, v3 is this, and I have gotten, let's say these two are, this is v1 tilde, this is v2 tilde. Think of v3 is in the 3rd dimension, okay? Now how do you find v3 tilde, which is orthogonal? So first I can project it onto v1 tilde, project onto v2 tilde, sum them, I get a vector which is here, right? This will be the vector, right? So I take the difference of v3 and this vector, right? So this vector minus this vector, right? So you take the difference of the two, I get the orthogonal. Do you agree? So what does that mean? It's v3 minus, I want to project v3 on v1 tilde minus projection of v3 on v2 tilde will give me v3 tilde. Now we can verify that v1 tilde, v2 tilde and v3 tilde are orthogonal. How do you verify? You take the inner product and see if they are orthogonal, right? You will get 0 or not. You can easily verify this. Okay. Do you want me to verify or you will verify? So how do you generalize this as Gram Schmidt's? Now I can just do this, right? Suppose I have Vn, okay, and I can do this, right? So what happens to Vn tilde, which is Vn minus, I have to sum all the projections, right? So I'll sum it from I equal to 1 to n minus 1 because I have tilde V2 tilde for V3. So projection of Vn on Vi tilde, right? Do you agree? So how did you get Vi tilde? Well, recurse. This is recursion, right? So maybe I'll instead of Vn, I'll do this. Okay, I'll write it as Vj. This is Vj. Okay, this is Vj. Okay, so basically J is 1, 2, etc. n. If I substitute J equal to 1, I get back the first step. J equal to 2, I get the second, and so on. Okay, this is a simple orthogonalization procedure. Nothing fancy or anything, right? So purely based on our high school geometry. We just abstracted it out, right? We just generalized some of the things. That's all. Okay. So if you are given, this is called Gram Schmidt's, right? So this is nothing but Gram Schmidt's, right? So Gram Schmidt's orthogonalization procedure. So how do you get orthonormal? So first of all, you have, let's say, V1, V2, etc., Vn. You apply Gram-Schmidt's orthogonalization to get V1 tilde, V2 tilde, and so on, Vn tilde. And then if you want to get orthonormal, all that I have to do is normalize, right? So what should I do? V1 tilde divided by 2 norm, and so on, Vn tilde divided by 2 norm of Vn tilde. So I get an orthonormal vector. Okay. Okay. So one thing to note here is that what is this? So let me recollect this. So what is this? How do I write this? V3, I have to project it onto V1. So first V1 tilde. So it's V3, V1 tilde divided by V1 tilde, V1 tilde, V1. Okay. Remember, it's some constant times V1 tilde. Sorry. Projection of U onto V is some constant times V. Okay. So keep that in mind. Okay. Now, what is QR decomposition? So QR, that's easy, right?